Hi, I'm Dick Van Grunsven, founder of Van's Aircraft and primary designer of the RV kit planes. I'm here today to share some good news about laser cut parts. They are conclusively safe to use in aircraft structures. When Vans first became aware of cracks forming around the edges of dimpled laser cut holes, we reacted with caution by offering to replace the laser manufactured parts we had supplied with many kits. We ceased laser cut parts production and stopped shipping kits with laser manufactured parts. Shipment of kits could not be resumed until we were able to produce replacement parts made on our CNC punch presses. Due to the sheer volume of parts affected, months passed before normal shipping could be resumed. To validate our earlier confidence in laser cut parts and our decision to outsource them, we resumed aggressive accelerated life testing of joints riveted using laser cut holes. This process is known as fatigue testing and consists of applying simulated flight level loads repeated hundreds of thousands of times to test coupons or samples until such time as they eventually fail by cracking. This is vaguely similar in principle to bending and rebending a paper clip wire until it breaks. From these test results, we made airframe service life projections. We tested literally hundreds of samples by applying loads in all foreseeable loading cases, multiple times for each case. Our testing soon revealed that there were different kinds of cracks, generally classified as manufacturing cracks and fatigue cracks, just as I mentioned. Manufacturing cracks are those that have been observed around dimpled countersunk laser cut holes. Our testing has shown that these are overwhelmingly passive when present in aircraft structures. These cracks don't elongate and lead to failure. They don't reduce the strength or expected life of the airplane. Van's engineering staff has prepared a very detailed video presentation that explains the results of our laser cut parts testing. This presentation has been viewed by a team of civil aviation officials who were pleased and reassured by our findings. In addition, 4 knowledgeable, experienced, and concerned kit industry people recently viewed the presentation and toured our test facility. The following is a summary presentation covering the laser cut hole testing performed by Vans. It covers the essential information you want and need to know. For those wishing to see an in-depth review of our testing disciplines and methods, a longer and more detailed presentation is available. It is linked at the beginning and end of this shorter form presentation.
Welcome, my name is Ryan Johnson. I have Brian Hickman with me here from the engineering department. Today we're going to show you a condensed form of a more detailed presentation. We'll have a link to that detailed presentation at the end of this segment. We're going to show you today that laser parts have a negligible impact on the safety in RVs. And overall, we're going to show you the testing that we went through to come to that conclusion.
We predominantly make parts through the CNC punch press process. In late 2021, there was a significant demand on our production system. So we underwent testing to approve laser cutting as an alternative. There's significant capability in outsourced providers. We went through testing and determined that was suitable. Later, concerns arose that required further analysis due to irregular holes and cracking dimples.
There are 3 ways that we looked at the data and analyzed the problem. We went through accelerated coupon testing, also looked at airframe analysis, calculations, etc., and something called residual strength testing, and that's what we're going to show you next.
Accelerated life testing is really based on a small coupon level, really testing the details of these components. They're done with high loads for hundreds of thousands of cycles so that we can produce statistical data sets that force fatigue damage and create fatigue cracks, and then we can make comparisons among different variables, methods, thicknesses, etc.
This is, we're just showing you a coupon running in our fatigue test machine there. This video runs. It's a machine that pulls in tension and compression. There are several variables that we looked at which changed over time as we explored those variables. We also went to an independent contractor to help us, whose background is in this area of metallurgy and fatigue testing and used them to also build out this variable set. And after looking at that outside vendor, there were a lot of coupons that were tested to test the different facets, and showing you some of those results here.
So effectively, what we learned through this testing is that the fatigue performance was not impacted by these dimple cracks, these manufactured cracks created at the time of assembly. There were only a handful of instances where this cracked dimple connected with any fatigue cracking in test, and through that, there was no statistical detectable difference in the performance of these holes. So this chart explains a large group of data and is comparing laser cut to punched holes. This is a statistical tool. They'll highlight the lows, highs, and kind of the variability of the spread of the data. This specifically is the flush 3/32 rivet in a 0.025-inch thick aluminum. This is our most common rivet hole configuration, especially in these laser cut components. And what we're doing here is we are then refining the data to predict the onset of fatigue cracking in a single hole. So the units along the bottom here, the x-axis, are in airframe hours, but they're under a very extreme use case. Realistic flying predicts roughly 10 times higher what we would truly predict a fatigue crack onset to be for that single highly loaded hole. As we compared this, we were also running samples of punched coupons. They developed fatigue cracking in effectively the same way. These components were not influenced. The mode of cracking or when it developed did not statistically change between the two components.
Looking at the crack there in the picture, you can see that the crack did not progress again to the manufactured crack, but it cracked through the stress field. And looking at that stress field in a different way, this is the predominant way in which you would see cracks happen in RVs. Historically, if you look at our service bulletins, et cetera, the stresses are higher at the rim of the dimple, just due to the way the skin transfers those stresses into the dimple. And they're the dominant driving factor in determining where that fatigue crack will occur. Realistic loading and fleet experience shows us that that's where the crack will occur. And our previous fatigue testing in years past has also shown that to be true. It's good to note here that the skins were never laser cut, and that's where we expect these cracks to form in RVs. And we get into more detail in this in the longer presentation. Looking at how we developed the loads that we applied with the fatigue test machine and accelerated testing and used in our analysis, we went to a couple of different resources. AC 23-13A gives guidance on converting data back and forth between accelerated coupon testing and the real world. So we looked at it in two different segments, one for use in a flight school, and then we also looked at EFIS data from actual flights in aerobatic RVs. We use that EFIS data to come up with our own conversion curves in the same methodology used by the FAA. So we're using real world data to come up with real reduction factors.
This is an example of different use cases. So as we look at these reduction factors and convert, the aerobatic fatigue case is significantly more damaging than a more normal general use or flight training, which is more damaging than that. As we predict things and need to look at the fatigue performance of certain details and holes, the most dominant factor in that and when something will crack is how the airplane is used or abused. To be conservative, we assume a significant amount of aerobatics are used in the aircraft. So these calculated service lives for these holes are given in units of an airplane that is flying half of its time in aerobatic flight, which is dramatically higher than any known case. 30 minutes of every hour, effectively 2 professional airshow routines every hour of flight. And that has a very dramatic reduction in the performance of those holes, and that leads to significant conservatism in this data. This is another way of looking at the data from these holes. So this has a projection from these data points based on how they will perform under different loads. In fatigue, as the stress or the load is reduced, the life dramatically increases. This is, again, that group of flush riveted 0.025-inch thick aluminum samples. And we can see how these data points and their predictions as versus load dramatically increase to completely unreasonable numbers. This chart ends at 100,000 airframe hours of half aerobatic use. And if we look at this blue line, that is showing that the average RV rivet loads are below this line. In reality, the average loads are far below that line. The highest load we have in any RV wing is 150 pounds at a 3/32 fastener. Realistic use, if we were to change the scale effectively for a average RV use case, would expect 10 times higher life. So if we look here at our 150-pound highest load in the wing, project it down to that 13,000 airframe hours under that very conservative use case, we can then multiply up to roughly 120,000 hours for what we would expect is still a conservative RV type of flying for that single hull. Again, that's the onset of cracking from the highest load of that peak load hull. I believe the next highest load is down at 110, 120 pounds.
It falls off dramatically. Yeah, it's the inboard portion of the wing. And it's good to remember here that we all know that we're not flying, out of every hour, we're not flying RVs half the time, conducting an air show, aerobatic routine. This is an important slide. It's talking about what was replaced and what we recommended for replacement. And all of this testing was pointing at us being sure and wanting a safe RV and determining what we needed to replace in the airplanes. All of our testing indicates a long service life on the parts, whether they were laser cut or punched. From a standpoint of safety, we've recommended parts for replacement here at Vans Aircraft. Though all our testing estimates a very long service life out of punched and laser cut parts, we're recommending the replacement of certain principal structures, parts that have low levels of redundancy and are critical to the integrity of the aircraft, specifically those that are difficult to inspect. They integrate with primary flight controls and are under high loads. This recommendation is based on the limited real fleet experience of those laser cut parts. This is an exercise in extreme caution. Replacing these few components will ensure that any unidentified factor cannot cause serious safety risk.
Residual strength testing verifies the redundancy in our structures as we can simulate damage and compromised components. This test, we took laser cut components and progressively failed internal structure, these laser cut parts, simulating a fully developed crack, compromising their structural performance and major attachments to the wing spar. We went through this test progressively, going from the highest loaded, highest stress components, working our way as the load will redistribute under certain failed conditions, and continued to test through many configurations, over 20 configurations. We failed webs, flanges, individual rivet holes, all in the highly loaded places where we would expect fatigue damage to occur first.
As you can see in that picture, we've failed the rib entirely across. This disconnected the rib's ability to carry any shear load into the main spar web. Another test that we conducted at Vans Aircraft was cycle loading of the full structure. This was to a full limit load with a half reversal, simulating one cycle simulates 1 hour in a flight school. Tell us a little bit more about that test, Brendan.
Yeah, so this test is done in a wiffle tree arrangement. That is something that allows you to very realistically apply a distributed load, span-wise and chord-wise, and insert the correct amount of bending and torsion. And if you mechanize it, you can get this repetitive loading, these repetitive cycles to build fatigue damage quickly, and in that simulate an aircraft that has experienced a long service life and try to identify if any issues will appear.
In conclusion, let's discuss the 3 different ways in which we conducted these tests, Brian. Accelerated life testing. Testing coupons.
Yeah, accelerated life testing. We were able to take a conservative approach, evaluate many, many variables and dozens of combinations to develop the worst case, most sensitive combination.
We had the input of the third party.
We had the input of the third party both before and throughout this testing program.
We also backed up our assumptions on what parts were recommended for replacement with calculations, finite element analysis, real world loadings, looking at how the airplanes realistically, the number of high load events that would occur.
Absolutely. A real detailed view on the stress analysis and highlighting and really taking a careful look at any place with any elevated stresses, those that we suspect would be more susceptible to fatigue.
We looked at an RV-12 and how it would perform in a flight school, the most highly stressed member, the stabulator.
Exactly. Applying the most realistic distributed loads many thousands and thousands of load cycles to simulate very aggressive advanced fatigue damage.
Over 30,000 times cycled to limit load, 30,000 hours as a representation in flight school. And moving on to residual strength testing.
This residual strength testing, it proves the safe design of these structures. There are certain components in here that we design at low loads with redundancy. These components, should any factor have been missed, will certainly perform their intended function, even with highly developed fatigue cracking, which we fully don't expect to ever occur. And these are not subtle, small cracks. This is a large scale, easily inspected, and frankly, impossible to miss levels of damage. Right. Yeah, and the aircraft will perform its intended function, safely fly, and safely land, even under this very advanced damage.
The point of that test is we don't have the field experience yet.
Absolutely.
To know. And it's a fail-safe.
It's somewhat of an extreme test. And a fail-safe is a good word. It's really it's a demonstration on the rigorous structural design that's in these aircraft.
Normally, under a test like that, you're only required, if you follow the FARs, to fail the primary principal structure. But we failed secondary structure inside of a wing. That's what was laser cut, part by part. And we encourage you to look at the long presentation to see that more in depth. Overall, this is a safe combination. It's a three-legged stool, so to speak. And we feel that we provided the safest way to move forward over the lifespan of your RV.
I hope that you enjoyed this and found it to be as informative and reassuring as I did. From this, I would be totally at ease flying in an airplane built with laser-cut parts. Since we have always prioritized safety and realized that you need to be confident beyond doubt, we will provide replacements for all laser-cut parts that we have recommended be replaced. Affected kit owners will be notified and advised about the process for replacing affected parts. Viewing the full-length video will no doubt answer many of your questions. If you have additional questions regarding laser-cut parts, they can be submitted via the form linked below. We will collect and provide answers to common questions on our website through the end of January. Thanks very much for your attention. I look forward to speaking to you again soon.